Krepel, Dr. Krepel, so for the next presentation on studies on the advanced fuel cycle for fast and thermal molten salt utilizing thorium at Paul Scherrer Institute in Zurich.
Okay, thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. I will try to be a little bit shorter than 30 minutes, but probably not so much. First of all, I would like to thank organizers for this wonderful opportunity. Second of all, as the first speaker of co-organizing institution, I may welcome you here once again, and thanks for coming to Switzerland. And if you allow me, I will spend just 1 minute to introduce a little bit the history of Paul Scherrer Institute. As many good things which started here in Geneva, although the history of Paul Scherrer Institute is related to Geneva through the very famous conference of peaceful use of atomic energy in 1955. You may know that the American delegation did the effort and brought a working reactor for this conference. And it was mainly Mr. Scherrer who convinced the Swiss government that they should buy it and keep it, that it's nonsense to transport it back from Switzerland. And 2 years later, in 1957, it was more or less sited in this building. Paul Scherrer Institute is on the Aare River, 10 kilometers from the German border. And the reactor is not anymore operating, it's decommissioned. However, the spent fuel is still here. As a matter of fact, the central spent fuel storage for Switzerland is next door of PSI. And the reason for that is that 4 from 5 currently operating reactors are in the 30 kilometers radius from Paul Scherrer Institute. Okay, so I would like to introduce our motivation for MSR research. I will be probably repeating several things, but I will try to put them in different perspective. Our research directions, then already finished studies. We did some simple studies with the students, and at the end, some new ideas and outlook of our projects. So the motivation, okay, two or four typical points. Excellent neutron economy, liquid fuel doesn't need fabrication, flexible fuel cycle, and MSR can be designed as inherently safe reactor with reduced risk. I will go one step deeper in each of these points. Okay, the excellent neutron economy was shown many times already here. This is a little bit different perspective. You have here the capture probability of uranium-3, plutonium-9, and uranium-5, and other 2 fertile materials in case of interaction with neutrons. And as you can see, it's really uranium-3 which makes the thorium cycle so interesting. The liquid state, of course, brings a big advantage, mainly because we heard many times here about the hard gammas, and the hard gammas are coming from the thorium-2 decay chain. Nevertheless, the half-life of thorium is very, very long. So that's the reason why we can, we don't have the sample anymore. We could have the sample in this room. The difference is that once you create thorium-2, you more or less accelerate this decay chain because the half-life of uranium-2 is 70 years. So you get much faster and much bigger amount of these hard gamma emitters. Uranium-plutonium cycle, on the other hand, is industrial established. If you want just recycle plutonium, everything is more or less ready. You may have some problems with americium and curium because to fabricate pellets with curium may be difficult. Okay, and if you have liquid fuel, these issues may be at least mitigated by the fact that you have liquid fuel. The flexibility, okay, apologizing, next time showing eta chart, but I would like to point here the difference for the eta if you use different neutron libraries. JEF 3.1, very optimistic, ENDBF 7, a little bit less, and this is the area where the fast spectrum MSR may operate. So there is a need to cross-check these data before we can get more serious. Okay, then MSR as an inherently safe reactor with reduced risk. This slide may raise some discussion. It's qualitatively using the farmer's curve, where you have a probability of incident and consequences. And if you have solid fuel reactor, you are somewhere here. You have very, very low probability that something very, very serious may happen. This is the case of Fukushima, and even if you will use natural circulation to improve the stability of your barriers, you will just move this point a little bit towards left. The question is if it will be convincing for public that you change your probability from 10 to -5 to 10 to -6. If this will convince the public that this way you avoid Fukushima again. On the other hand, with liquid fuel reactors, it's a technological must to remove volatile and fission products. So we are removing these elements. We are decoupling them from the chain reaction. We are decoupling them from the major decay heat source. So we are reducing the consequences of possible severe accident. On the other hand, we are missing barriers, and this we must admit openly. So we are moving this point, let's say somewhere here. The same issue may be illustrated a different way, but before I will go for that, maybe we should say here two things. First of all, even if you will have natural circulation to protect your barriers, and even if you will have accelerator, you must still admit that the probability that you melt the core is bigger than 0. And second of all, even if you will have molten salt reactor, which is perfectly safe and whatever, you will work with gaseous and volatile fission products inside of your cycle. You will need a containment. So those are probably two things which we should admit from both sides. Okay, and then the second illustration I wanted to use is a barrier principle, which doesn't work so good as for the light water reactor, especially because okay, the fuel matrix is probably equivalent with the solubility of actinides and fission products in the salt, but the cladding is equivalent here to primary circuit boundary. What is here also is the helium bubbling, which removes and decouples the volatile and mobile fission products from the fission and decay heat source. It is serving as a pseudo barrier because it is acting during nominal operation, and when it comes to severe accident, thanks to daily removal, you reduce the consequences. Okay, known drawbacks, of course, structural material corrosion, radiation embrittlement, graphite may have limited lifespan if applied. Reprocessing techniques are relatively complicated, and chemical treatment of the salt may be related to possible proliferation risk. So our idea is, we may say stupid, so let's design MSR with so appealing fuel cycle and safety characteristic that it will be worth to overcome the drawbacks. Furthermore, going a little bit more to the detail, we are ready to sacrifice part of the freedom of neutronic designing because you have liquid fuel reactor, and you can do so many paper reactors that let's not optimize just the neutronics. Let's look if we can help the other issues, and we are ready to sacrifice part of it to help the solutions. And the third idea, okay, since we are involved in education also, we would like to integrate master students, PhD students, and postdoc works into a students' reactor designing project. The project may be in the future extended for other fields because PSI can do other different researches and also supported by senior researchers. But this is now open point. Several very first steps. I will not really go to details. We have some calculation tool. We modify them for the liquid fuel. We program some new tools to be more efficient and fast. And also looked preparing our tool for transient analysis of the MSR, so especially the open foam. We are in the learning phase, but it seems like an excellent multi-physics tool to simulate these innovative reactors. What we also did, we established a kind of cooperation. We became an official observer of the EVOL projects, and we started to collaborate with Politecnica di Milano and Technical University of Prague. And we start already and finish already some studies. I will go into details for the first two. So we used our fuel cycle procedure for spectral study, and then its 0D version for a little bit more advanced study. And the novelty of these studies, because you can find such a study in literature, is that we were looking for different salt-graphite ratios, so different moderation ratios in the molten salt reactor. And for each case, we try to make the reactor critical by core radius, and we find out the equilibrium composition. For given reprocessing scheme, we were looking on equilibrium. So this is the future in 1 or 2 centuries, which is too far, but can help us already now to understand the physics of the reactors. Furthermore, we looked on 2 different graphite geometries. The first one was kind of classical channel, so you have graphite block with salt channel inside, or you may have graphite blocks inside in the salt. So classical and inverted geometry. And we evaluated the safety parameters for both geometries. And as I said, we tried to make the core critical for every salt graphite share by core radius, and we use Hastelloy as a material around the reactor, so not really a reflector. The salt was adopted from the EVOL project of the MSR specification. So now I would like to show you 3 results based to this study. The first result is an excess reactivity. So you have known conclusions you can breathe in fast and thermal spectrum. Here you can see it on the graph. We neglected fission products at this moment, but you can see that for the equilibrium core, you have roughly excess reactivity of 20,000 PCM, which is eaten, or the neutrons are absorbed by uranium-3, 4, then the rest of uranium, a little bit of plutonium and minor actinides. In the fast spectrum, in the thermal, it's very similar, but at a certain moment, the absorption of salt and graphite became important, and you can't go any further. But as you see, the other elements are not absorbing so much here, but unfortunately, the graphite doesn't enable this point. And both are possible. Okay, what is not possible is probably the epithermal one. I guess the colleagues from TerraPower call it the valley of deaths. So to operate a reactor in such a spectra is probably not really good. But this point and this point may be working, but for thermal reactor, of course, you need much more frequent reprocessing than for the fast. Second result are the masses. So first of all, the relative mass of uranium-3 and thorium-2. Of course, in a thermal spectra, you need much less uranium-3 than in a fast spectra. So it's only 2% of uranium-3 compared to thorium in thermal spectra, then compared to 14% of uranium-3 in fast spectra. Of course, if your uranium-3 thorium-2 share is below or above the curve, you may be breeding or burning. This is basic physics. But you may also see that the heterogeneity effect makes some difference. So the classical and inverted channel geometry has some influence. From the other masses, the conclusion is that the absolute mass of uranium-3 in both thermal and fast reactors is very comparable. Actually, you have 1.8 tons just in the core. I didn't account for the circuit. You have 1.8 tons of uranium-3 in the core. You have just 2 tons in the fast reactor. So the relative share is much higher in the fast reactor, but the absolute masses, thanks to the core size, because the thermal core is much, much bigger, are comparable. But you can also see from this chart that the other absolute masses, looking on this point and this point, are also comparable. Just the thorium, of course, the thorium was 15 tons here, something like 80 tons here, because this ratio must be strongly different, so you have much more thorium in thermal system. You have slightly less uranium-2 in thermal spectrum, but what is interesting is just half. It's not an order. So you may have 80, now let's say uranium-2 primary axis in kilograms. So you have 4 kilos of uranium-2 in fast version. You have 2 kilos in thermal version. And if you allow me to comment on this chart, I didn't plot protactinium-1, which was discussed here already, but 90% of the uranium-2 is created from end-to-end reaction on thorium-2, and this reaction goes through protactinium-1. And if you would plot the protactinium-1 masses, they are comparable, relatively comparable to uranium-2. They are slightly lower, especially in thermal spectrum. They are, let's say, 1/3 or 50% lower. But protactinium-1 is in the chain of uranium-2 creation. Okay, the third result, thermal feedback coefficients. What we found out, not a big surprise, salt thermal feedback coefficient is always negative. It's composed from Doppler and expansion effect. The graphite thermal feedback coefficient may be positive, especially if you have inverted this channel geometry. So the graphite may expand, and it may really make the coefficient positive. But on the core level, those dark green curves, these effects are relatively weak, and it's negative in the classical geometry case and slightly positive in the inverted geometry case. The reason why we don't have a positive effect on the core level is that we didn't use graphite reflector. If you would use graphite reflector, it will be slightly positive for the thermal spectrum. Okay, now I have one slide to introduce the EQL0D study. The previous study covers just a selected line, and EQL0D was programmed to be more efficient and fast. So the previous study is just this line in a 2D space where you have salt channel radius and salt share in the core. So this tool was used to study heterogeneity of the core. So we did something like this. We changed the salt share, but also the size of the channels. And the first result is that the heterogeneity is strong. So you see here now the K infinity as a function of the channel size for different shares of the salt in the core. And the previous study is represented by this curve. So it seems like arbitrary results. Nevertheless, if you use uranium-3, thorium-2 as a spectral index, both these studies with EQL3D and 0D gives the same trend, so there is some coherency. And the most interesting result we find out when we try to make the channels much bigger, going up to 1 meter channels, we find out that many of the salt share cases converge to the same K infinity. It's probably not a big surprise. But the question is here, what is the spectrum for this big channels system? And this was leading us to something like hybrid spectra MSR. The idea is simple. You have salt, which is subcritical in the fast spectra, and you put a graphite, massive graphite tube in the center, which will be acting as a central driving thermal zone of the subcritical fast salt. It doesn't need to be massive graphite tube, because you may have some problems with thermal resistance of that, and you may need to have a lattice. And to illustrate that you have more or less thermal driving zone, this is the thermal flux distribution along this axis, epithermal and fast. So majority of the salt is irradiated by the fast flux. And the reason why we call it hybrid spectra is, okay, yes, I forgot to mention the advantages which you may have from this. It may reduce irradiation of the asteroid. It's acting like subcritical reactor, so the flux is falling down faster than in critical reactor. It may reduce the fissile material needed for starting the reactor, and in a big pool, it may localize the fission reaction. But why we call it hybrid spectra is shown on this figure. So here you have core radius and energy of neutrons, and you see it's really two different spectra and on two different places. Okay, the last part of my presentation I would like to dedicate to reprocessing, because if you want to design, you need to speak about reprocessing. And short overview, okay, you have fluorination, which is very strong. You can use it for solid fuel reprocessing. You can use it for molten salt mixtures. You can use electroseparation processes. You can use molten salt liquid metal reductive extraction process. And you must remove gaseous and volatile fission products. This will be always there. This is a technological must, and this may be the main safety advantage. What is also interesting is this method, which is very trivial. And if you speak about thorium fluorides, this may give really a strength. It was tested in Oak Ridge during the MSR. They were changing the fissile isotope of uranium during this experiment. And I think within 3 or 4 days, they managed to fluorinate all the salt and replace the uranium-5 to uranium-3. So it's robust. It can be done remote, probably. And our idea is recycling without carrier salt reprocessing. So inverting the aim of all reprocessing methods. So you want to always remove fission products. They are usually the last which comes out if you do reprocessing schemes. And you must use all the methods. And from a classical point of view, it is disadvantage that uranium is coming first. So in this case, let's invert it. Let's make it an advantage that uranium is coming first. And let's recycle just uranium and throw the rest. Okay, throwing is probably too strong here. The rest may be reprocessed with long delay, and the clean salt may be reused in the same reactor or in another reactor. So you may wait 20 years before you clean up the rest, but you recycle uranium immediately. The carrier salt for that may be without enriched lithium-7, maybe sodium fluoride, barium difluoride. But as was present recently by Charles Forsberg, lithium-7 may be cheap, so it may be even lithium-7 salt. We have an illustration for two-fluid approach using this method. So you have a blanket, you use continuous fluorination to get uranium out. You use this uranium to maintain the core critical, and then you have here more or less open cycle for the carrier salt, and you recycle just uranium by volatilization. This exchange may be done online, batch-wise, or once in a time, replacing all the salt, maybe even together with the Hastelloy, because if you will have two fluids, this wall will suffer, and you will need to replace it relatively often. So maybe you will be replacing the salt with the Hastelloy at the same time and just recycling uranium, taking new carrier salt and going on. So you must process this, but you may do it in 20 years. You don't need it. You don't need to do it immediately. Another illustration of this idea, you can have a pool. You can use this hybrid spectra idea to localize your fission to the center, and again use this recycling without reprocessing. The question may be what will be left in the salt, which will be stored for 20 years. And we did some study looking on how the composition evolves. I will not go to detail. These values are for equilibrium, but the dynamic, if you start from fresh fuel with uranium-3, is such that in 1500 megawatt thermal reactor, after 20 years, you create something like, I don't know, 15 kilograms of neptunium-7 and 13 kilograms of plutonium-8, which may be even volatile if you want. You may recycle them by volatilization. So it seems acceptable. In the equilibrium, it's a little bit more, like 4 times more. That seems OK. Ongoing steps and outlook. We have some master thesis and new PhD student. We have plans what he should check, what he should evaluate. And if you would like to meet our student, which should start his work at PSI next week, is the kind gentleman which is handing you the microphone for the questions, which I'm now open for.
Thank you very much. Thank you. First question. So this is the student.
Yes.
I thought I understood 2 things about what we're trying to do. Is we're trying to design a nuclear of the future, which means that a nuclear systems that can be deployed on very large quantities. We're talking about 1,000, 10,000s of stations. And we also know that this type of system, whatever it is, has to address the three main issues of nuclear systems. That means the safety, the disposal of waste, and proliferation. I don't understand how this type of system can deal with all those things. First, for what concerns the waste, we know that thermal systems don't address the issue of the waste. The question of safety is also maybe an issue. I saw that you talked about positive temperature coefficients, for example, and proliferation in a thermal system extracting almost pure protactinium-233, I think is an ideal proliferating system. So what's your answer to this?
Okay, I will try to remember these 3 points. First one, I start with the waste. You see that the waste of thermal and fast reactors, they don't differ so much. And thanks to the feature of uranium cycle, you have uranium-3, which has 10% chance of capture in both spectra. So the uranium-4 mass is equal for both systems. Then you capture with high probability a neutron, create uranium-5. And uranium-5 is better fissile in thermal spectra. So up to here, you may be creating less waste, but we speak about uranium still. Then you go to uranium-6, okay, the capture probability is slightly different. You go to neptunium-7, which also equal, let's say, capture probabilities, and then you start with plutonium-8. These are equilibrium masses, so in equilibrium you may have 5% of plutonium in your reactor compared to the uranium, and uranium-3, and there are 2 tons of uranium-3, so we speak about 100 kilos of plutonium-8. And you can volatile it, you can recycle it if you want. So if there will be some waste which will be not recycled, it should be beyond plutonium. But to create something beyond plutonium in thorium cycle, that's not really easy. So I would say, if you care about neptunium and plutonium, we can increase the volatilization process to volatile them too, and it should be safe. And then the rest is really ready for vitrification. The second question was the proliferation. You can continuously volatile your blanket, but anyway, the thorium is in the blanket, irradiated by the neutrons in the same manner for the capture, like for the end-to-end reaction. So you can't separate end-to-end reaction and capture of thorium. So the blanket will provide also uranium-2 through the protactinium-1, which with another capture creates uranium-2. So even if you will very fast fluorinate your blanket, you still will be producing uranium-2. You may add graphite, or you may moderate the flux outgoing from the reactor, and then your blanket will really produce weapon-grade things, probably. It will drop the uranium-2 share. But you can produce weapons with any blanket. You can put the blanket in any reactor. You can put uranium blanket in a reactor, reprocess it very fast, and you produce weapon-grade material. So I don't see big difference between thorium and plutonium cycle, but I'm not an expert for that. I can just tell you the shares, and an expert must tell me, okay, this is good. If I would like to build a bomb from uranium-3, maybe I wait for Mirha and ask for a salt loop in the center and produce the bomb there. I would not relate it to critical MSR. It's too complicated to build a bomb, sorry. and the third one?
Third one was referring to the positive void coefficient for the core calculation. That was true. Sorry, positive temperature coefficient.
Yes,
not void.
We speak about graphite. The expansion of graphite is highly complicated. There are different graphites. There are different graphite producers. The expansion coefficient may differ in direction in the graphite. The expansion coefficient may differ according to temperature. It may be shrinking for certain temperatures. It may be expanding for some. It may not be expanded at all. In the previous thermal MSR studies, it was assumed that graphite is not expanding.
Okay. Question?
Hard to answer.
I have a question. It's about the safety issues for this system.
Mm-hmm.
Have you looked at those? I mean, this system is what temperature it is operating at? We
adopted the MSFR parameter, so you can expect the same 650, 750.
Yeah, but if it goes to in an operational transient, it goes to higher temperature, and you get release of cesium and other fission products coming in. So maybe you have removed them yesterday, but today's products could be coming out.
Yes, this is a good point. I would say if we should go serious at PSI, this may be exactly the direction, because it may be important for the Switzerland, which is small and cannot afford releases. This may be a direction where to go and check these characteristics. If you say that at 750 cesium is not released and at 1,000 it is released, then it is a problem. Yes.
It is. It is released at 1,000.
The question is
and there's noble gases too.
Yes, but just let me ask another question. The cesium, isn't it kind of decay product of xenon?
Huh?
Isn't the cesium decay product of xenon?
Not only.
No.
Xenon
is
direct production.
Gas.
Okay, yeah, you can directly yield it, but partly it's also decay product. Huh?
Okay. Next question, Dominique. After. Microphone. Just wait for the microphone, please.
Sorry, I come back to proliferation issues. I would like to remind what I said yesterday. Sorry to say that, but I have developed methods for evaluating proliferation resistance to any nuclear system, which is available on the internet and which is called SAPRA, Simplified Approach for Proliferation Resistance Assessment of Nuclear Systems. It's available on the internet. I mean, it's a that report detailing the methods for evaluating proliferation resistance. First point. Second point, I remind that this method has been applied by Bruno Pelot, who was the former responsible for safeguards and proliferation question at the IEA, which was the former Director General of Safeguards Department. So he knows exactly what he's speaking about. He applied these methods. He published documents, once again, unfortunately, which is not public, but the main conclusion of these documents, of course, it depends of scenarios, of types of reactors. You have to enter in details in scenario of proliferation. You know, as you said, you can put in any reactor uranium fuel, you know, natural uranium, and make very good plutonium by removing it, or whatever. If you have neutrons, you can make good plutonium, whatever the reactor is, okay? And okay, it's the easiest way to proliferate. So there is no absolutely proliferation resistant system, more or less. There are more or less proliferation resistance. But the main conclusion that, roughly speaking, all systems have the same level of proliferation resistance if it is safeguarded well. And if it is safeguarded well, the proliferation resistance of nuclear system is very high. There has never been in the past, one example, or otherwise tell me which example, of deviation of civil facilities, which is under safeguards with, you know, just, you know, stealing fissile material and making nuclear waste. But no example in the past. No.
Mm-hmm. I may just comment that you are right. But there is a slight problem with the liquid fuel reactor. If you work at IEA, go for inspection to a reactor, what you like is, so you have here 300 assemblies of these serial numbers. So you check, this assembly, this assembly, this assembly. But in liquid fuel reactor, your breeding can be 1.5 or 1.55. And suddenly the mass flow is a little bit less controllable. So this may be an issue. We may openly say that, but...
Okay. Processing plant, you have
the same.
The same.
The same. Exactly the same. Exactly. So what is the conclusion? If you design MSR, you are designing at the same time more or less reprocessing plant.
The Japanese with Wakashimura,
yes.
They are manipulating pentons.
Yes.
Well, yes.
Of course. No. I like MSR. We would like to design it, but there are some points to discuss.
The best proliferation is not to manipulate the fuel too often, I think. So whether it is in a reactor or in a reprocessing plant. I think there was a question from gentleman behind.
You answered a question on the positive feedback from thermal expansion of graphite. Did you also recognize a term of positive feedback term from the temperature of thermalization of the neutrons, shifting the spectrum towards slightly harder.
Okay, I didn't show the breakdown, but the kind of integral or the curve which I showed is composition of several effects. First of all, there is spectral effect, which you are now mentioning. You have a Maxwellian neutron distribution, which is shifted, it's just hardening with the increase of temperature. And you shift it to an area where the fission cross-section of uranium-3 is slightly higher than uranium-2 capture, and there is also kind of a peak. So you are introducing positive reactivity just through the spectral effect. So there is no Doppler, but there is shift of the spectrum, as you are saying. But it may be compensated in case of full core simulation by leakage. We didn't have a reflector here, good reflector, so leakage was compensating for that. And in case the graphite expands, it's also changing in thermal system the fuel to moderator ratio. And if these reactors are kind of under-moderated, it depends if the expansion brings more salt or release the salt from the core. To release the salt is wrong because it's under-moderated, so it brings reactivity. So what is better to have classical geometry, which when you expand the classical geometry, you make the channels bigger, there is more fuel. It sounds crazy, but it's better because it's under-moderated system.
Can you say there are too many uncertainties which lead to reactivity effects?
Yeah. Yeah.
Can we say that there are so many uncertainties which can lead to reactivity effects?
Uncertainties, you mean?
Uncertainties in which you were just mentioning.
Yeah, depends. I would say if you go for graphite, put it in a pool, as it was shown here, make it leaky, and if it will be leaky, then the coefficient will be negative. If you will make a reactor 4 by 4 meters, moderated by graphite, it may be positive. Yes.
Okay. Question? If not, so I would like to thank the speaker again for his nice presentation. And